All right, welcome back. Today we're diving into a really fascinating paradox in machine learning called overfitting. It's this idea of what happens when a model, well, when it gets a little too smart for its own good. So, let's just jump right in with a question I want you to mull over for a second. What actually happens when a model becomes too good at learning? I mean, that sounds totally backward, doesn't it? How can being too good at something ever be a bad thing? Well, to really get why, we need to pin down exactly what we mean by overfitting. Okay, so here's the deal. Overfitting is basically when a model stops learning the real pattern, the signal, and instead it just starts memorizing all the random noise in the data. Think of it like this. The model sees all this random stuff, this residual variation, and mistakenly thinks, hey, this must be part of the important structure, when it's really not. And that leads to the classic giveaway. You get these amazing, super high accuracy scores on the data you used for training, but the second you show it some new data, something it's never seen before, its performance just tanks. It completely falls apart. It's kind of like a student who just memorized the answers for one single test, but never actually learned the material. They'd fail any other test, right? Same idea.
Okay, I get it. This might still feel a little bit abstract. So, you know what? Let's make it super concrete. Let's actually see what this looks like.
So a really great way to visualize this is to try fitting a curve to a bunch of data points. Just imagine we've got some data and it generally follows a nice, simple curve. But like in any real-world scenario, there's a bit of random noise, these little errors scattered all around it. First up, let's look at what happens when our model is just too simple. We call this underfitting. Here, we're trying to draw a straight line through data that's clearly curvy. As you can see, it just doesn't work. It totally misses the real trend. This is what's known as having high bias. The model is just too rigid, it's not flexible enough to capture the truth. Okay, now for the Goldilocks model, the one that's just right. Take a look at this smooth curve. See how it beautifully captures the general trend of the data points? It's smart enough to see the real pattern while ignoring all that random noise. This is what we want. And here it is. Overfitting. When the model is way too complex, you get this wild, chaotic, wiggly line. It's twisting and turning like crazy just to hit every single data point perfectly. It hasn't learned the trend at all. It has just memorized everything, the signal, the noise, all of it. And you can imagine, this model would be absolutely useless for predicting any new points. So seeing all three of these together really shows this fundamental trade-off we have to deal with. We've talked about underfitting and overfitting. You'll often hear these linked to two other terms, high bias and high variance. So let's break down exactly what those mean. Right, let's nail this down. High bias, that's our underfitting problem. It means the model is too simple. It's making these really strong but wrong assumptions about the data, so it just consistently misses the mark. Then you've got high variance. That's our overfitting problem. This means the model is so complex and sensitive that it reacts to every tiny bit of noise. Its predictions are flawless for the data it's already seen, but for anything new, they're all over the place, completely unreliable. Okay, that visual is great. It makes things crystal clear when you're just fitting a simple curve. But let's be real. In the real world, we're dealing with these huge, massive neural networks. You can't just plot a simple line for a model that has millions or even billions of parameters. So how on earth do you spot overfitting in a beast like that? Well, since we can't just look at it, we have to diagnose it using the data itself. What we do is we test the model on the data it was trained with, and then we test it again on a completely separate set of data that it's never seen before. We usually call this a development or dev set. And by comparing the errors on both, we can figure out what's going on. For instance, if your error on the training data is super low, but the error on the dev set is really high, bam, that's your red flag. The model isn't generalizing, that's overfitting. If both errors are high, well then you're probably underfitting. The sweet spot, the goal, is to get both of those error rates nice and low. So it kind of feels like the most powerful, most complex models are the ones most at risk for this, right? Which leads to the big question, why? Why are these huge deep learning networks so prone to overfitting in the first place? The answer really is in their DNA. I mean, a deep neural network can have a staggering number of what we call learnable parameters. We are talking millions, sometimes even billions of these little weights and biases spread across all its layers. And that incredible complexity, it's a total double-edged sword. On one hand, it gives the network the power to learn these amazingly subtle, complex patterns. But on the other hand, it gives it more than enough firepower to just straight up memorize all the noise in the training data if you're not careful.
Okay, so let's do a quick recap of the big takeaways. 1. Overfitting is when the model learns the noise, not the signal. 2. The key symptom? It aces the test it studied for, but fails every other one. Great on training data, terrible on new data. 3. We can picture it as that crazy, wiggly line that memorizes every single dot. And 4. We spot it in the wild by comparing how it does on data it's seen versus data it hasn't. It really all boils down to this balancing act. A model needs to be complex enough to actually learn, but not so complex that it just decides to memorize everything instead.
Hey, if you got something out of this explainer, it would be awesome if you could hit that like button, maybe share it with someone else who'd find it useful, and of course, subscribe so you don't miss our next deep dive.
And I'll leave you with one last thing to chew on. If a model's greatest strength, its sheer complexity, is also its greatest weakness, its biggest risk, then what is the true limit of what AI can ever reliably learn? Think about that.